Lesson 3, Uniform Speed and Velocity. 3.1, Scalars and Vectors. There are two kinds of measurements in physics. Measurements where direction does not matter, and measurements where direction is important. It's critical to giving the measurement meaning. Up until now, you've mostly been used to using the first kind, where direction isn't important. This first kind of measurement, where direction does not matter, is called a scalar quantity, or a scalar measurement. Measurements where direction is important are called vector quantities, and they're going to become very important in physics in the upcoming months. Examples of scalars include mass, time, length, and speed, which makes sense because if you have a 5 kilogram mass, it's not like you have a 5 kilogram mass to the north. You just have 5 kilograms. Examples of vectors include velocity, which is how fast you're going and which way you're going, acceleration, which matters which direction you're speeding up in, and force, which matters which way you're pushing and which way you're pulling. For questions with vectors, or with scalars, your answer must have the following pieces. It must have correct magnitude, so it must have the correct amount or number to get full marks, and it must provide a unit. And this magnitude must also have correct significant digits. For example, the measurement d equals 15 meters, or distance equals 15 meters. The magnitude is the number 15 with 2 significant digits, and the unit is the meter. Both pieces are important for a correct answer. For questions with vectors, you have an extra piece. You have the direction piece, and your answers must have all 3 pieces to be correct. These are magnitude, which is the amount or the number part of the answer, the unit, and you put direction in square brackets to show which way the vector is pointing. Your magnitude must also have the correct significant digits. An example of a vector written out is the store is 150 meters to the north. The magnitude is the 150 meters, the unit is the meters, and the direction is the north in square brackets. On your data sheet, the symbols for vectors and scalars are differentiated with little arrows over the letter. This allows us to tell which kind of symbol shows a vector and which kind shows a scalar, and it tells you what to do in your calculations. For example, v is speed, which is a scalar quantity. The same letter v, but with an arrow over it, indicates instead velocity, which is a vector quantity. Calculations with vectors and scalars use different techniques. If you have a vector, you have to do one kind of addition technique, and if you have a scalar, you do the other. Adding scalar quantities together is actually quite easy. It requires no new skills. You can just add the numbers together. Vectors, on the other hand, require a vector addition techniques. Vector arithmetic, or adding vectors, is a bit more tricky. This is because you also have to consider the direction in your calculation. For now, we're only going to worry about one-dimensional vector addition. Later on, you're going to learn how to add two-dimensional vectors and possibly even three-dimensional vectors. But for now, our vectors are always going to be in the same plane or pointing the same or opposite directions, which is one-dimensional. The first method for 1D vector addition is to draw a picture using vector arrows. So you draw arrows to show the length and direction of the vector, indicating size and direction. You line up the tip of one arrow with the tail of the other. This is called tail to tip or tip to tail vector addition. It's not as hard when it's only one-dimensional and it seems quite simple, but it's a good technique to learn now while it's simple, so that way for two-dimensional vector addition, it's already something you understand. So for example, 15 meters east plus 25 meters to the west. We draw the 15-meter arrow pointing in an east direction, and then from its tip, we draw the 25-meter arrow to the west, and it's longer to show that 25 is longer than 15. The answer goes from the tail of the 15 to the tip of the 25, and just by eyeballing it, we can see that it's 10 meters to the west. This final answer is actually called the resultant. And this answer is found by drawing a resultant arrow from the tail of the first vector to the tip of the second. The second method for vector addition is to use plus or minus signs to indicate direction, in your calculations. The direction signs can be told by looking at our Cartesian coordinate plane. This is something you should be familiar with from math. Now, north is the direction that's up and south is down, east to the right and west to the left. We can also say east is a forward direction and west is a backward direction, for now. North and up are positive. South and down are negative, just like the positive and negative y-axis. East, right, and forward are positive. West, backwards, and left are negative. Here's an example. 125 meters to the north plus 95 meters to the south. We'll start by writing out the question again so I can show you how to use the plus and minus sign instead of directions. Cross out the direction and replace it with the corresponding sign. So north becomes positive and we have positive 125, and south becomes negative and we have negative 95. The answer is positive 30, but this is not proper vector notation. To get the proper vector notation, we always have to change the plus or minus sign back to a direction. Since we were working in a north-south direction before, we assume that the positive direction indicates a north. And we also give it a unit of meters. So we have 30 meters to the north as a final answer. 3.2. Distance and displacement. In physics, distance and displacement are both measurements of length. Length is a measurement that's determined in meters. But they're actually very different ideas. Distance is defined by how far you go in total. Direction doesn't matter to distance, so it's a scalar quantity. Displacement does care about direction. Displacement is how far you are from your start point and which direction you are from where you started. Displacement is a vector. Because distance is a scalar, the symbol is d just on its own. Displacement is a vector, so its symbol is d with a little arrow above it to show that it's a vector and that it's different from distance. The unit for both distance and displacement is the meter. Here's an example to give you an idea of the big difference between distance and displacement. Let's imagine a little bug, and it goes on a journey walking around your note paper. And it's quite a convoluted journey. It can't quite decide which way to go, so it just wanders around. From the point of view of distance, we would count the whole trip. For example, this bug's distance might be something like 1.5 meters at the end of the trip, all the way around your page. Displacement only cares about the little place between where it started and it ended. In this case, displacement might be as small as 0.25 meters. And it's got a direction. It's down from where it started. Distance is the total amount walked, regardless of direction. Displacement only takes into account the amount of length from start to finish. Here's an example with numbers. A girl who seems to be pacing walks 5 meters north, then turns and walks 10 meters east. Then she walks 5 meters south. I don't know why she's doing this. Maybe she's doing it as a physics experiment. In this trip, what is her distance and what is her displacement? We'll start with distance because it's easy. Distance is a scalar. And because distance is a scalar, we can just add the numbers together. 5 plus 10 plus 5 equals 20 meters. We don't have to worry about direction. Displacement is a vector, which means that you have to use vector addition methods to combine the 3 directions she walked. Method 1 involved drawing a tail-to-tip diagram. To do this, we draw the little 5 meters she walked north as a shorter arrow, the 10 meters she walked east as a longer arrow, and the 5 meters she walked to the south as a similar length arrow as the 5 meters north. And we can see the north and south cancel each other out, and all that's left is a 10 meter to the east. So we would say her displacement, D arrow, is 10 meters to the east. Method 2 is when we do math with the plus or minus signs. To do this, we write out the vectors, adding them together, 5 meters north plus 10 meters east plus 5 meters south. And then we convert these directions into plus and minus signs. North is plus, east is also plus. So we have plus 5 plus plus 10 plus minus 5 meters because south is negative. Combine these all together, we get plus 10 meters. But we have to change this positive sign back into a direction, and we take it to be east because that's what our diagram suggests it should be. So displacement is 10 meters to the east. 3.3, speed and velocity. We'll start this lesson by looking at the quantity speed. Speed is a measurement of how fast an object is moving. Speed is a scalar quantity. This means that we don't use direction in our calculations for speed. Direction doesn't matter to speed because it's a scalar. The symbol we use for speed is lowercase v, and the unit is the meter per second, m/s. Most of the time we're looking at objects that change speed. In the real world, objects don't really travel at constant speed. So we often are calculating for average speed. Average speed is when an object is moving at a series of different speeds or a bunch of different speeds in a particular time frame. We can calculate average speed. There's a formula for average speed. It's probably one you've seen before. The formula we use for average speed is V average equals delta D over delta T. This little triangle symbol that you see there is Greek letter delta. Delta is placed in a formula to signify that we mean change in the symbol it's next to. Delta D, for example, means the total change in distance. Very important in this definition is the word total. Total means we add up all the distances traveled. Delta T means the total change in. The delta reminds us that it's a change in time. This is measured in seconds. Before we move on to some examples, let's also look at the quantity velocity, which is slightly different than speed. It has a different definition and it's calculated slightly differently. Velocity is how fast you are moving or you are leaving your start position. And the direction you are moving. Key in this definition is the word direction, which tells us that velocity is a vector. We do have to consider direction when we're doing calculations for velocity. The symbol that we use for velocity is also a lowercase v, but in this case with a vector arrow over top. The unit is the meter per second. Average velocity is similar to average speed. Average velocity is calculated when an object changes speed or changes velocity during a trip. And there is a formula we can use to calculate the average velocity. The average velocity formula, V average equals triangle D or delta D over delta T. Delta D is the total change in displacement. Delta T is the total change in time. Now here's an example. A car travels 500 meters north in 105 seconds. And then makes a U-turn and travels back 300 meters to the south in 87 seconds. What is the average speed and velocity of the car? The first thing we do is calculate the total change in distance. This comes from the 500 meters and the 300 meters. 500 meters plus 300 meters equals 800 meters. Because distance is a scalar, we could just add the numbers together. The total change in displacement does have to take into account direction. This is 500 meters to the north plus 300 meters to the south. Changing the directions into signs, we get positive 500 meters plus negative 300 meters, negative because of the south. This equals positive 200 meters or 200 meters to the north. The total change in time is 87 seconds plus 105 seconds. This equals 192 seconds. The average speed is calculated by change in distance over change in time. This is 800 meters divided by 192 seconds. This equals 4.2 meters per second. The total velocity average is equal to displacement over time. The displacement was 200 meters to the north. Divided by 192 seconds, the total time doesn't change. This equals 1.0 meters per second to the south. Don't forget to put a direction on your vectors. The south is an important part of the answer. Here's another example. Let's think about a dog running around a field, and it doesn't run in a particularly straight line, it just runs around and has a lot of fun while it's doing it. In this pretty crazy trip, there's just a very tiny displacement. Just the distance from start to finish is the displacement. Here's the question. A dog runs around a field. Even though the dog travels or covers 400 meters distance in total, he only ends up 2.5 meters to the south of his start point, or of where he started. This trip takes the dog 300 seconds. The average speed is the change in distance over time. This is the 400 meters divided by 300 seconds. And this gives an average speed of 1.33 meters per second. The average velocity is change in displacement over time. This is only 2.5 meters to the south divided by 300 seconds, which is 0.0083 meters per second to the south. So even though the dog is traveling at a good average speed throughout the trip, he's traveling at a very slow average velocity. This is a good example of how velocity and speed can actually be quite different for the same trip. This is because average velocity is how fast you are traveling from your start point. If you're running around a lot but not getting particularly far from where you started, your velocity is not going to be very fast. One more example, and this one's a little bit trickier. A car travels at 100 meters per second for 25 seconds, and then slows to travel 50 meters per second for 75 seconds. What is the average speed of the car? Well, the first thing you're going to want to do, and it's the first thing most students do, is this. The first thing you're going to want to do is calculate V average equals 100 plus 50 divided by 2, because that's how you've always calculated average. But this isn't going to work. Don't do this. This would work if they're traveling for the same amount of time, the two speeds, but they're not. The car spends more time traveling at the slower speed. It spends more time at 50 meters per second than at 100 meters per second. So the formula wouldn't work like that. Instead, you need to find the total distance. This is because the formula specifies that the average speed is total distance over total time. We can rearrange v equals d over t to get d equals vt. The distance traveled in 100 meters, then, is 100 meters per second times 25 seconds. This is 2,500 meters traveled at 100 meters per second. The distance traveled for the 50 meters per second is 50 meters per second times 75 seconds. And this equals 3,750 meters. So the total distance is 2,500 meters plus 3,750 meters. This equals 6,250 meters. So the average velocity, total distance over total time, average speed, is 6,250 meters divided by total time, which is 25 plus 75 seconds. This equals 63 meters per second, which is the average speed for the trip. Now, often in physics, we'll actually just look at constant speed situations, even though they're not really realistic in real life. And these are defined as uniform speed. Uniform speed is when an object travels at the same rate without changing speed, without changing direction. Same speed, same direction is uniform motion. For example, a car traveling in a straight line on cruise control would be traveling with a fairly good example of uniform motion or uniform speed. In this case, if an object is traveling with constant speed, we have a special case. Then speed equals velocity. They're the same thing. And this is because there is no direction if it's traveling uniformly. There's no direction change, so velocity would end up being the same as speed. Also, the average velocity in this case would be equal to just the velocity, or the speed, and that's equal to d over t.